In this video, we're going to take a look at the mean value theorem. And so our mean value theorem says if we have this continuous function on a closed interval from a to b, and it's differentiable on its interior, so the open interval a to b, then there exists at least one point c in that open interval such that the derivative at c is equal to f of b minus f of a over b minus a. So what this is saying, the intuition of this is we have to have a point in the interior that is equal to the slope of the line between the two endpoints, right? So f of b is the y value at the endpoint b, f of a is the y value at the endpoint a, and b and a are the x values at those two endpoints, and so we have the change in y over the change in x. So that is the slope. All right, so let's go through and prove this. Let g of x be equal to f of b minus f of a over b minus a. Right? So that is the slope of the line between the two endpoints a and b. We can use the point slope formula, so x minus a plus f of a. So this is the equation of the line that connects the points a comma f of a and b comma f of b. All right, so we have the equation of the line connecting those 2 points, and that is g of x. Let h of x be equal to f of x minus g of x. We can make the observation or the note that h of x is continuous on that the h is continuous on the closed interval from a to b, and it's differentiable on the open interval from a to b. What else do we know? We can also observe that what is the function value of h at a? Well, if we were to evaluate g of a, when we plug in a up here into this function, when we plug in a for our value of x, this is going to become 0, so that all goes away, so we just have f of a. So h of a is going to be equal to f of a minus g of a, but g of a is equal to f of a, so h of a is equal to 0, and h of b would be equal to f of b minus g of b. But what happens when we plug in b up into this function? When we plug in b for our value of x, this becomes b minus a, and so that b minus a will cancel with that. So you'll have f of b minus f of a plus f of a, so the f of a is canceled, and you're left with just the f of b. So here we get f of b minus g of b, but g of b is also f of b, so we get 0 there as well. So h of a is equal to h of b. And this is going to allow us to apply Rolle's theorem. So by Rolle's theorem, we have a point, there exists a C in the open interval from A to B, such that H prime of C is equal to 0. Then what do we know? What is H prime of C? Well, H prime of C is equal to F prime of C minus G prime of C. So F prime of C equals G prime of C. But what is that G prime of C? That value for G prime of C is equal to F of B minus F of C. Minus F of A over B minus A. Therefore, the derivative of F at C is equal to F of B minus F of A over B minus A for some C. In that open interval from A to B. And that is it. We have proven the mean value theorem. So that says there's a point in the interior that has a derivative that is equal to the slope of the line between the two endpoints. With this, I tend to think of Rolle's theorem as a consequence of this. That's the way I usually think about it, where if the value at the two endpoints are equal, this gives us 0 here. That's not really a great way to think about it because we used Rolle's theorem to prove this. So if we think about Rolle's theorem as a consequence of this, then we actually have some circular logic. And so be really careful there. Even though that's seems like a solid intuition, it being a consequence, we can only think about Rolle's theorem being a corollary of this if you can prove this independent of Rolle's theorem. All right. We will talk to you in the next video.